Okay, so today we're going to go over basically what makes up an atom and then how that was discovered. So who discovered it, how, when, why, where, all that good stuff. Okay, so what you'll have to do today is you'll have to watch this video that I'm making right now, or you can go on Plato and just go through the entire slideshow here for models of the atom. Actually, I shouldn't say the whole thing. It's up to slide 18 for today. But I'm also going to be going over some of my own slides here for the unit one here. So I included this slideshow as well, and we're basically going to be going over these 8 through 14 and a little bit of these first two. Okay, with that, let's get started here. So atomic theory. So basically, an atom. So an atom, so they don't even go over this. Sometimes they just jump right into assuming that you know what an atom is. So I'm going to assume that you don't know exactly what an atom is, but an atom is the smallest unit of matter that has the properties of a given element. Okay, and when we say that, what an atom is made up of protons, neutrons, electrons. So there's protons and neutrons in the nucleus or the center of the atom, and then there's electrons surrounding the outside of the atom. Okay, right now we don't need to know. Next lesson in part 2, you'll learn how to find out how many protons there are, neutrons are, and electrons there are in a given atom based on some given information. Okay, we're not going to talk about that right now. What we're going to talk about instead is how did we figure out that there's protons, neutrons, and electrons in the atom? Okay, so basically it's a bunch of scientists that figured it out. And if we start here, the first person to really coin the term atom was this guy named Democritus. So he's an ancient Greek philosopher, and he actually coined the term atomos. And the term atomos here actually meant uncuttable. Okay, so in 400 BC, he coined the term atomos. Okay, oh yeah, and as you're going along here, you might want to fill out this Google Doc. So this is part of the assignment here, the Google Doc. You're going to write the date, and you just follow the directions right here. The date, give any, draw a picture of the atom model. Don't draw a picture. You can't draw a picture on here. You can just copy and paste one from the internet if you like. If you can do that, if you have the ability to do that. Otherwise, just type out the notes in this section here in each one of these sections. Okay. So you want to do that as we go through today. Sorry, I'm a little bit all over the place today. A little hyped up, a little ready to go here. All right. So anyway, so Democritus, he was the first one to coin the term atomos all the way back in 400 BC. Okay, he thought atoms were indivisible, indestructible, and that every substance was made of different atomos. So, like this fork was made of different atomos, this can was made of different atomos. That was part of my lunch. That's why I'm all hyped up. Got some Red Bull there. This was made of different atomos. Everything was made of different atomos. Okay, there was very little science involved in this. It was still in the realm of philosophy. This actually idea really didn't hold too strongly for too long because people like Socrates, Aristotle, they still believed in the 4 elements, right? Earth, wind, fire, air. And that's not really the truth. But Democritus was the first guy to really come up with this. Okay. After Democritus, this is really the father of the atom was John Dalton. So he was born in 1766. So he's the father of modern atomic theory. His theory was based on the law of conservation of mass and definite proportions. So in around 1800, so when he was like in his mid 30s, he came up with this idea, this atomic theory. So there's 4 parts to the atomic theory. The 4 parts are: number 1, all elements are composed of tiny indivisible particles called atoms. Number 2, atoms of the same element are identical. Atoms of different elements are different. Atoms can combine physically or chemically in simple whole number ratios. And chemical reactions occur when atoms are separated, joined, or rearranged. Atoms of one element cannot become another element through chemical reactions. Okay, so if we look at and we figure out which ones of these are true today, still hold true today. So all elements are composed of tiny indivisible particles called atoms. That's actually not true. right? That's not really true because atoms are made of protons, neutrons, electrons. They are divisible. They are divisible. Okay, so that's not really true. Number two, atoms of the same element are identical, and atoms of different elements are different. That's actually not true either. Okay, because we can actually change the number of electrons and the number of neutrons. If we change the number of electrons, we call it an ion. If we change the number of protons, we call it, sorry, not protons, neutrons. If we change the number of neutrons, we call it an isotope. If we change the number of protons, that changes the identity of the element. That changes the element totally. And we can actually do that. We can actually change the number of protons. Nuclear decay or nuclear fission causes, or nuclear fusion can cause the change in protons in an element. Okay. But number 3 and 4 are still true today. Atoms can combine physically or chemically in simple whole number ratios. And number 4, chemical reactions occur when atoms are separated, joined, or rearranged. So that is the definition of a chemical reaction: atoms joining, separating, forming new compounds. Okay, so combinations of atoms. All right, so that was John Dalton. Okay, he was the father of atomic theory. Next is J.J. Thomson. So J.J. Thomson conducted this experiment called the cathode ray tube, and what he noted in 1897, he did this, and he noticed that there was particles that would flow, basically electricity. Like this electricity is electrons flowing, right? So they're flowing, and he noticed that they reacted to a magnetic field, so they have a charge to them. And he basically said, okay, well, the charge, we're going to call that a negative charge. Okay, so he discovered electrons. J.J. Thomson's cathode ray tube discovered electrons. Okay, now he knew that atoms themselves were neutrally charged. So if there was negative particles, there must also be positively charged particles as well. And he just assumed, okay, well, if there's negative particles, positive particles, they must be kind of all mushed around and just evenly dispersed throughout the atom. And he called this his plum pudding model. If you think about like bread pudding with raisins, the raisins are all in it. Well, it was kind of like the negative charged particles all dispersed throughout a positively charged, like bread pudding. You know, the electrons are the raisins, and the actual bread is the positive charge. So that's what he thought. That's what he thought was going on. But the next person to come along was Ernest Rutherford. So Ernest Rutherford conducted his gold foil experiment. So his gold foil experiment, and he did this in 1911. So it's consisted of basically an alpha particle emitter. Alpha particles are basically just helium atoms that result from the decomposition of a larger atom. Ow! My cat just jumped on me. Jerk. He scratched me. So anyway, so the alpha particle emitter, it shot off these highly charged particles at gold foil. Okay, and what he assumed was that if these atoms were dense, positively charged things, and that they could not, that they were just dense little solid things, that the alpha particles just bounce right back to him. So he figured, all right, if it bounces right back, then the Thomson model is probably correct. But what he noticed is actually most of them actually went straight through the gold foil. Okay, and because most of them went straight through the gold foil, he assumed that actually most of the atom is empty space. Okay, some did deflect though. Some came, a few came right back, and then other ones deflected off in different directions. And so what he decided was, okay, you know what? There's probably a dense positive center surrounded by mostly empty space. Okay, and if you actually really think about it, an atom is actually like 99% empty space, or 99%. We don't really know what makes up an atom. Okay, it's really confusing because it's like, well, everything is made of atoms, and then but atoms are mostly empty space. So aren't we just all empty space? We're all nothing. We're nothing. You know, that's like, kind of like a weird thought, right? Like what else is there, right? So really, we don't know. We don't know what else is there. There's some theories, but we don't really know exactly for sure what's going on. If you were to actually, if an atom had the nucleus the size of a pea, if the nucleus was the size of the pea, the radius would actually be the size of a football field. So think about putting a pea in the middle of a football field, and then the atom being the size of the football field. That's kind of crazy, right? Because most of that is just empty space, and that is like what an atom is. Okay, and then the reason that atoms don't just pass through one another is because the interactions, the charges, the negative and positive charges, are very, very strong. You know, like when you take two magnets and you push them to get Jack. Sorry about that. Jack doesn't want me to do my presentation. He wants me to pay attention to him. Kicked on my keyboard. But anyway, so if you think about you putting two magnets together, right? Two magnets with opposite with identical poles, and they won't go together. They push apart. That's basically what's happening when two electrons come together. They push apart, and two protons come together. They push apart. What holds protons together in the nucleus is actually the neutrons. The neutrons help eliminate that repulsion, right? And then yeah, so atoms are crazy things. Atoms are crazy things, right? So next. So now we know that the atom has a dense positive center surrounded by mostly empty space. The next person to come along was Niels Bohr. And what he said was the atom that in 1913, what he found was that electrons actually occupy energy levels. So the electrons aren't just floating around randomly in the atom. They're not just in any old space, but they're actually in energy levels. So he thought they were in shells. Like you ever see like a Russian nesting doll? So the electrons are in different shells. Okay. And what he said was that the atoms are actually rotating, or sorry, the electrons are actually rotating around the nucleus like planets around the sun. Okay, so this is what he thought. This is what he thought. And the reason he thought this is because he noticed that atoms always gave off the same distinct color when they were excited. Okay, so you excite atoms by putting electricity or heat into it, and it always gave off the same electricity or light, and that's because the atoms were jumping between energy levels. We'll talk more about that a little bit later when we talk about electron configurations and atomic orbitals, but we're going to hold off on that for right now. We're just talking about the different atomic models for the moment. Okay, and then the last person to come in was Heisenberg and Schrodinger. In the Plato thing, they only talk about Schrodinger, but I like to talk about Heisenberg too because Heisenberg was part of this work. In 1925, and this happened, and Heisenberg was only 23 at the time, and he won the Nobel Prize for this in 1932. What he said was the electrons aren't actually rotating around the nucleus like planets around the sun, but instead they're just in those energy levels and they move randomly. So they're in that space. They are in that space, but they move randomly. Okay, and why his idea was accepted over Bohr's was because he was able to calculate the amount of energy that would be released by an electron when they were excited. Okay, and really the Bohr model and the Schrodinger model, very similar in idea. It was really the math that separates these two, and the math is very, very complicated. It involves calculus, so it's kind of hard to explain in general terms, right? But as best we can explain it is that Bohr thought they rotated in like planets around the sun, and Heisenberg and Schrodinger said nope, they don't rotate. They move pretty randomly, but you can find them in a certain space. They are in a certain space. Okay. So that's all the atomic models. Let's look at the tutorial. Like that was my tutorial. So I'll kind of run through this tutorial really quickly. I don't think they give as much good information in this tutorial. That's why I kind of did my own, and that's the way I always do it. But again, Democritus, smallest atom indivisible. Another 2,000 years before this idea took shape or changed, I should say, should change. And then Dalton came up with his atomic theory. I don't like the way they didn't really list out 1 through 4. his ideas, so that's why I did mine. If you want to look at this more closely, feel free to. Dalton actually noticed that when you combined hydrogen and oxygen and you made water, or actually the opposite, when you took water and you split it in the hydrogen and oxygen, he realized that it was always the same proportions. You always got twice as much hydrogen as you did oxygen. Okay, so he realized that there's 2 hydrogens for every 1 oxygen. It's always that way. So he saw that. He also came up with the law of like definite proportions. Um, and Lavoisier did that, actually. Lavoisier did that, and then Dalton kind of took that and came up with his atomic theory. Okay, Thomson, again, the cathode ray. And he came up with the plum pudding model. So this is all what I said. Rutherford Guilfoyle experiment. Feel free to watch all this stuff, but it's everything that I went through. Bohr with the energy levels. And then the modern atomic theory, the modern atomic theory came based on Erwin Schrödinger and de Broglie equation. Again, there was actually a whole bunch of people. De Broglie, Schrödinger, and Heisenberg all kind of worked on this modern atomic theory. Okay. There is this here, this lesson activity. You don't need to do it. It's fine because I asked you. I'm just having you do the assignment that I gave you, and that's fine. Yeah. So that's it. That's it. We're gonna go over the structure of the atom next time. All right, and that's all I have to say. If you want to check out the simulation for the different atomic models, that might give you a better idea. But like I said again, you do not need to fill out these things. This might help though if you go through this. So totally up to you if you want to do it or not. All right, so now that you did that, make sure you go through and fill out this worksheet right here. There's a copy made for each person, so do the best you can to fill that out, and we'll do part 2 tomorrow. All right, enjoy the rest of your day. Bye. Hey, stop it, Jack.